Okay, we'll start today's class. I'll share my screen, okay? Okay, today we'll be mainly looking for the view factor. We'll be solving problems related to view factor. Okay, view factor in radiation.
Ma'am, this is last session.
No, I think we have one more session. And there is also another extra class, I think, for 1 hour. That I'll be taking on 14th.
Okay.
Yeah, so the last class will be on heat exchangers and all, I think. And last day, 1 more hour I have kept so that that on 14th I have kept so that just for some revision or some leftover questions, something like that. Okay, we'll start with today's class. Um, I'll just go through the uh, formulae what will be needed in today's class. So the sir has already spoken about the uh, radiation exchange between black bodies and also gray surfaces also. So for black bodies, the net radiation exchange between n, if there are n number of black bodies, then the net radiation exchange can be given by this formula. Now this is for n black bodies. For gray bodies, Q net I is given as summation I to j equal to I to n, sorry, 1 to n, AI Fij ji minus jj. Now this is also equal to ebi minus ji divided by 1 minus epsilon I ai epsilon I. So this is just like the resistance formula. This is written according to resistance. This is the driving force and this is the resistance for the radiation. Then for two concentric surfaces, sorry, coaxial disk, this was done in last week. I mean this week to last week lecture. If these are the two coaxial disks, then we can say that this Fij, this is I, this is J, then Fij will be equal to d square by 4l square plus d square. Now L is this. L is the length between both, sorry, the distance between the two disks, and d is the diameter of the larger disks. This is the formula. And then for two surfaces, two parallel infinitely long surfaces like this, These are infinitely long surface and also parallel. So Q can be given as long parallel plates. So we'll start with today's um, numericals. So the first one is a long V-shaped part in heat is heat treated by suspending it in a tubular furnace with a diameter of 2 meter and a wall temperature of 1000 Kelvin. So this is the V shape is this V part V shaped part is this is heat treated in it is suspended in a tubular furnace. So this is the tubular furnace. The circular cross section is given. It's somewhat like this tube with a diameter of 2 meter and a wall temperature of 1000 Kelvin. The V is 1 meter long. That means one part is 1 meter, another part is 1 meter. So L is equal to 1 meter and has an angle of 60 degree. This is 60 degree. If the wall of the furnace, that means this wall of the furnace and the surfaces of the part may be approximated as black bodies. So both are black bodies and the part is at an initial temperature of 300 degrees Kelvin. That means this part means this V part. This is at a temperature of 300 Kelvin. What is the net rate of radiation heat transfer per unit length to the part? So to this, how much is the net heat radiation? So for they have given some hints. For symmetry conditions, it is convenient to treat the system as a three-surface enclosure consisting of the inner surfaces of the V1. So the inner surfaces is considered 1, the outer surface is considered 2, both the outer surface is considered 2, and the furnace wall is 3. So this is 3. So there are 3 surfaces. So what have they asked to find out the net heat rate, right? So from reciprocity relation, we can write E1 F13 is equal to A3 F31. So reciprocity and symmetry relation you already know, right? This is the reciprocity relation for view factor. Now here one is this one, the inner side, the outer side is 2 and the bigger surface is 3. So from here we can say we also know A3. Okay. This A3 is how much? 1 was given as 1 meter, right? L equal to 1 meter. So this A1 is how much? For we are not considering the full area because it is per unit length. Anyways, we have to calculate per unit length, okay? And they have not given it as 3 dimension. It has, I mean, this 1 meter is only of 1 dimension only. Okay, so we calculate it per unit length. So if we calculate the area of this A1 or 1 surface 1, considering both the surfaces. Suppose the length is L, I mean not L, because this is L, so we can consider the length of the tube to be some X. So the area of this part, it should be, this side is 1, this side is 1, it should be 2L into X, right? This is the area. But since we are considering per unit length, so this we are cancelling. We don't need to write this X. So we can directly write this as 2L. This A1 as 2L. And this F13, this we can write as, this is the meaning that how much 3 is receiving from 1. Okay, view factor F13. 13 means 3 is receiving and 1 is emitting. The first number denotes emitting and emission, and the second number denotes receiving. So how much it is receiving, since there are two surfaces, one is this side and the other is left and right V surfaces, so each one is contributing, so it will become 0.5. For from symmetry relation, it becomes 0.5. Okay, so this becomes how much? 1L. And then we also have this A2F23 equal to A3F32. Now here this A2 will be same, because A2 is just the outer surface of this A1, means the outer side. So its length are also same. So it should be 2L. But A2 is the outer side. That means this side. So what 3 can receive the whole of A2 actually. But the A1 was inside. So some of the radiation, it is one of the side of the A1 itself is receiving. So it's not, 3 is not getting all of that. That's why it is only half because of symmetry. But for 2 and 3, relation between 2 and 3, whatever 2 is emitting, 3 can receive all of them. That's why it is 1. So this will become 2L. L means already it is given 1 in 1 into 1, it's 1. L is 1 meter and this is 2 meter. Okay, so now the net radiation is given by net heat radiation to the V part is given by Q net. This is of wall, that is furnace wall, and this is V part. So the net radiation the V part is receiving is everything receiving from the 3. Okay. So that is the total net radiation received by this V part. So instead of this A3F31, we can write as A1F13. Instead of A3F32, we can write as A2F23. Now from here, sigma is constant and this temperature difference also constant. You can take this as common. So sigma is 5.67 into 10 to the power minus 8 into the temperature differences. This was the outer surface was given as, I mean the furnace temperature is 1000 and the V surface is 300. And then we also have we have calculated this A3 F31 is equal to A1 F13, which is equal to 1 and plus 2. So A3 F32 is A2 F23. This is 2. So how much do you get if you calculate?
168722.11.
Tell in terms of 10 to the power 5 if you convert it in 10 to the power 5.
Option B.
Option B. So did you get this question, this solution?
Yes. But ma'am, please explain about the view factor which should be taken in F13 and F31. How to determine that both two terms? They are very confusing while solving the questions. Please
Okay,
explain that.
wait. So what they have asked, what is the net rate of heat radiation, net rate of radiation heat transfer per unit length to the part? To the part. Part means V. This V is, they are telling it as part, okay? That V-shaped part. So that means what it is receiving means what net radiation to the part. That means obviously the radiation is given from the this what is this called, this tubular furnace. So the total net radiation emitted by this tubular furnace is given by this. That means there are two surfaces, 2 and 1. To each of them, how much this 3 is giving. Okay. To 1, how much it is giving, how much 3 is giving to 1 is sigma A3. This is the total energy. This you get it right. Sigma A3 F31, and this is the temperature difference. Now already in view factor I have told that this the first number denotes the emitting surface and the second number denotes the receiving surface. So if you want to calculate from 3 to 1, it should be F31, right? F31. And the area corresponding to that is A3. Now same thing, this is for surface 1. How much 3 is given to 1? For surface 2, it should be A3 F32. That means 3 is the receiving, 2 is the, sorry, 3 is the emitting, 2 is the receiving. So you have to calculate this. This is how much 3 is giving to 2. This how much 3 is giving to 1. But we are not directly calculating A3 F31. We are not directly calculating A3 F32 because we know the other way around is easier. So A3 F31 can be written as A1 F13 for from the reciprocity relation. This is the reciprocity relation. From here we know this A1 they have given the length of one one arm of the V as 1 meter. So the other arm is also 1 meter, and since it is per unit length, we have not considered the two dimensional part. We are considering only what is on the screen, not inside and outside the screen. We have divided it by x, so it is 2 twice L, and F13 is how much 3 is receiving from 1 since it is inside surface. Now this surface, suppose if you consider it is emitting like this and 3 is outside here. So 3 is not receiving all of the surface because some of the rays are also going this side. It's not receiving all of the surface. Same for here, for this surface also. So from symmetry we can say that these two are same, right? These two arms are same. So from symmetry we can say that it is 0.5. It's not 1. 1 means everything you are getting. So this becomes 1L into 1 into 1, that is this 1 meter. Then same similarly from this, if we say 2 is the outer surface, outside one. So if the outer surface emits the radiation, that 3 can receive everything, all of the radiation. So it is 1. Now A2 is same only. It is the same surface as 1 only. The area is same, only 1 is inside and 2 is outside. So it becomes 2 into L, 2 meter. We'll continue to do more of these view factors today. Whole of all of the numericals on view factor only, so you'll get to understand. Are you clear with this? Okay. Now a flat bottomed hole 6 millimeter in diameter is bored to a, actually for this type of I mean exactly what you want to find out, write that first, and from there what you know, what you don't know, just sort that out. And here one thing is, I mean advantageous is this, you can use this reciprocity relation, and then you can find out. A flat bottom hole 6 millimeter in diameter is bored to a depth of 24 millimeter in a diffuse gray material having an emissivity of 0.8 and a uniform temperature of 1000 Kelvin. So if this is the material, this is the material. Okay. Now 6 millimeter diameter is bored. Suppose this is 6 millimeter diameter. This is bored to a depth of 24 millimeter. Suppose if it is L in a diffuse gray material. So this is diffuse gray material having an emissivity of 0.8 and a uniform temperature of 1000 Kelvin. So this surface, now this is like a hole, okay? Since it is bored, just like you're boring well inside. So this is a hole and it is bored till this um, length or depth. So here this we consider this as a hypothetical some area, okay? Suppose this surfaces, the inside surfaces are 1 and this hypothetical surface is 2. Now we make some assumptions here, that this surface area 2 is, it acts as a black body at 0 Kelvin. Since at 0 Kelvin, so we can say that EB2 is 0. Okay, and since it is a black body, J2 is equal to EB2 equal to 0. Okay, now determine the radiant power leaving the opening of the cavity. How much power is leaving this opening of the cavity? So how do you find this out? So we can draw a, here itself we can draw a, just 1 minute. So if you draw the resistance in this vertical way, we have this, Actually, it is from below. It should be 1. It should be 1. It should be 2. It should be 2. Now this resistance is equal to 1 minus epsilon 1 minus epsilon 2 divided by A2 epsilon 2, and the between one is due to the view factor. Okay, the view factor between 1 and 2. So the resistance in this, in between this, will be 1 by A1 F12, and last, this resistance will be 1 minus epsilon 1 divided by A1 epsilon 1. So if you write this resistances, EB1 minus EB2 divided by, now here this EB1 is this, this is the surface one. So and it has a uniform temperature of 1000 Kelvin. So we can calculate this EB1 as sigma T to the power 4, or T1 to the power 4. So 5.67 into 10 to the power minus 8 into 1000 to the power 4. Just calculate it, how much we get. Then from here we know
Five,
this epsilon 1.
56700.
Can you say a bit louder?
5,000, 15,600, 6,600.
Okay, you're telling about this. You're
Yes,
telling
yes.
about this EB1.
Yes, you.
Okay. Now for calculating this F12, we can calculate it as, now this is 2 and this is 1. This whole one is 1. This is this consider it as 1. So we need to find out this F12. Means how much 1 is emitting which is received by this 2. But do we know that, can we directly say this F12, or can we directly say this F21? F21 means how much 2 is emitting and which is received by this 1, means inside. So here in this case this F21 is equal to 1, because whatever 2 is emitting is all are received by this 1. So if we want to calculate, we know this now. So we can directly calculate this F12 as A2 by A1 into F21. Now A2 is given by this surface area, pi d square by 4 divided by A1 is pi d. So A1 is this. this plus this. So the bottom surface is again pi d square by 4 plus the curved surface area. Curved surface area is pi dl. So this into f1. F1 is 1. So if we calculate this, pi d will be cancelled. D by 4, D by 4 plus L. Is it correct? So D is 6 millimeter and L is 24 millimeter. So this is F12. Now from here, what else do you know? This EB2 is 0 because we have considered this as black body, the second surface as black body at 0 Kelvin. And since and epsilon 1 is given, this emissivity for surface 1 as 0.8. A1 we know, A1, A2, everything we know, but we don't know this. Okay, this emissivity should also be, since it is a black body, since it is a black body, emissivity is 1. Emissivity and absorptivity both are 1 for black body. So if we put it as 1, this part becomes 0. Alright. Now you just have to calculate this. Q becomes EB1. EB2 is also equal to 0. 1 minus epsilon 1. A1 epsilon 1 plus 1 by A1 F12. Now you have already calculated this EB1.
Show the emissivity, emissivity, the emissivity.
What? I didn't get it.
Ma'am, show the question.
Okay.
Option 1.
Okay. Yeah, it is option 1. We'll calculate the second part also. The effective emissivity epsilon E of a cavity is defined as the ratio of the radiant power leaving the cavity to that from a black body, having the area of the cavity opening and temperature. So the first part, it is the ratio they have given. Emissivity, effective emissivity is the ratio of the radiant power leaving the cavity. So this is what they have asked in the first question itself, radiant power leaving the cavity. So that is, we have suppose denoted it by Q. So we write it as Q. Now to that from a below is from a black body. So the same, not the same, but the radiate power from a black body having the area of the cavity opening and the temperature. Area of the cavity opening and the temperature of the inner surfaces of the cavity. The opening is this surface 2. So for surface 2, what is the radiant power? It is given by just sigma a to the power the t to the power 4. So sigma is always constant. It's a constant. A is the A2 because it is this is the opening and this is black body, and T to the power 4. Now the temperature is, since we have taken T equal to 0, but this temperature they are not asking to take. They have asked to take the temperature of the inner surfaces of the cavity. So T should be 1000. All right, this 1000 uh, inner surface was having a temperature of 1000 Kelvin. So if you calculate this, you get 1.58. This is watt, right? Then below will be 5.67 into 10 to the power minus 8 into A2 will be just pi d square by 4 into 1000 to the power 4. So this is epsilon. So you will get this around 0.98, and 0.98 is almost equal to 1. That means it is almost black body. We have already considered it as a black body, but this is the effective emissivity 0.98. So you calculate this, you will get, okay. You might have already got. Should I move to the next question? Okay, the next is a very long electrical conductor 10 millimeter in diameter is concentric with a cooled cylinder tube 50 millimeter in diameter whose surface is diffuse and gray with an emissivity of 0.9 and temperature of 27 degrees Celsius. So concentric means they're having the same, they're axially having the same axis, that means same center. So if we draw, first one is 10 millimeter, right? That means the electrical conductor is like this. This is 10 millimeter, suppose D1, and it is cooled with a cooled cylindrical tube 50 millimeter in diameter. This is the cooled cylinder. This is 50. Now this surface is diffuse and gray with an emissivity of epsilon 2 is 0.9 and temperature is 27 degrees Celsius. That means 300 Kelvin. The electrical conductor has a diffuse, so this is also diffuse and gray surface with an emissivity of epsilon 1 is 0.6 and dissipating, this is dissipating Q of 6 watt per meter of length, that is Q dash. Assuming that the space between the two surfaces is evacuated, that means this part is vacuum. Calculate the surface temperature of the conductor. So if you assume this as vacuum, that means there is nothing else. There is no convection and all. So that is the assumption made here. So this is only radiation we have to consider. Assuming that the space is evacuated, calculate the surface temperature of the conductor. That means T1 we have to calculate. Now it's the same. This also has three resistances. You can say Q is equal to Q12 is equal to sigma A1 T1 to the power 4 divided by T2 to the power 4 divided by 1 minus epsilon. Now if I divide this by A, both the numerator and denominator, how much I get? This is just simplification. You can directly calculate from here also. This Q12 dash is Q12 divided by L. Can you tell how much you get here? I think all are given. R1 R1 is the D1 by 2. D1 is 10 millimeter. T1 is okay. You don't know the T2. Sorry, T1 you don't know. So T1 you have to find out. T2 is this 300 Kelvin. Then 1 minus epsilon 1. Epsilon 1 is given as 0.6. Epsilon 2 is given as 0.2. And A1, A2 you can directly calculate. A1 is this small surface, smaller cylinder. This is A1 will be minus R1L. A2 will be 2 pi R2L. So L is anyways not given. So no issues since all are divided by L only. So just consider this unit L. Then F12. Okay, the only thing you need to find out is this F12. And Q12 is also given, right? It is 6 watt per meter. So how do you find out this F12? F12 means how much one is emitting and two is receiving. So one is emitting like this. So two is receiving everything. So it is basically equal to 1. So can you calculate T1 from here? This T1. Everything else is given. Are you getting anything?
Very last calculation, it takes time.
Huh?
It takes time. It
Okay, okay.
takes time. Last time.
I think there is some mistake here. This should be actually this numerator should be sigma t1 to the power 4 minus t2 to the power 4. There is no a, I think, right?
Yes, ma'am. So the calculation will be taking too much time for this extra part.
So if you do not consider this, then just multiply here a1, and also below if you multiply a1, if suppose this is not there, then it should be like this: 1 minus epsilon 1 divided by, if you multiply with a1, it should be epsilon 1 minus epsilon 2. Epsilon 2 should be a1 by a2 plus, this is anyways 1 only, so okay, it was a1 was here, 1 by a1 it is. So 1 by sorry, a1 by a1, so it will, this will become 1. So if I write this, it should become like this: epsilon 1 by epsilon plus 1. A1 and A2 is pi d, pi d1L divided by pi d2L. So L, pi will be cancelled, d1 by d2 will remain, and then you can simplify this thing. This one, it can be written as this one, epsilon 1 minus epsilon plus epsilon. So this will get cancelled. So this thing will only reduce to 1 by epsilon 1 plus this into d1. I'm writing it first again. Everything is gone. This will be 1. This will become 1 by epsilon 1. So this is Q12 if I consider it as, instead of A1 I can write this as 2 pi R1 into L, or pi D1L. So if it is Q12 divided by L, this should become 2 pi R1. You can write it as D1 by D2 or R1 by R2. Yeah, so this is the, you got this? This is right, right?
Yes.
So you calculate it, you will get this, you should get this around this 69 degrees Celsius. You got this one, no? Because the upper one does not have this A. Actually, the upper numerator is actually EB, emissive form, emissive power form, so it does not have area in its formula. So what I did, just I multiplied A1 with both numerator and denominator. In numerator it has just 8, and in denominator I have cancelled this A1 I have cancelled, then this A2 I have written in A1 by A2 format. Then after getting cancelled in the second part, this F12 is 1, view factor is 1, because the outer cylinder can receive all the radiation emitted by the inner cylinder, so it's 1. So it just, if I simplify that, it should become 1 by epsilon 1 in this part, and this part remains as this 1 minus epsilon 2 divided by epsilon 2 d1 by d2, or you can write r1 by r2 also. Then if you calculate per unit length, then from here the numerator was 2 pi r1 L, so L gets cancelled, so only 2 pi r1 remains, and the final form is this. Just write it and you see later, you calculate it later, you should get around this T you should get around, sorry, T1 you should get around 69 degrees Celsius. The next question.
Yes.
Concentric spheres of diameter d1 is equal to 0.8, d2 equal to 1.2 meter are separated by an air space, and have surface temperatures of T1 equal to 400, T2 equal to 300. So these are again concentric spheres, again having the same radius. So this D1 is, so this is D2. Bigger circle is D2, and smaller circle is D1 is equal to 0.8 meter, separated by air. So this is air, and have surface temperatures of T1 and T2. T1 and T2, 400 and 300. If the surfaces are black, what is the net rate of radiation exchange between the spheres? So the here F net radiation, again we can calculate as Same only. This has almost same formula as that of the previous one. 1 minus epsilon 1 a1 epsilon 1 plus 1 by a1 f12 plus 1 minus epsilon 2 divided by a2 epsilon 2. Just remember that in such cases there are these are three resistance system. Two are the radiation of the surfaces, this and this one, and one is due to the view factor between these two surfaces. So this is the view factor resistance, and these are the surface resistance from the surface. How much how much they're emitting from there, whatever is the resistance, that is this surface resistance, and this is the view factor resistance. Again, if you simplify it, you get the same way, but here one thing you have to consider is the area. That case was a cylindrical case, so the area was pi dl or 2 pi rl, but here the area of sphere is 4 pi r square. So you just have to make sure that this is correct. So the same thing if you do here, how much it will come. Here they have not asked for per unit length, just direct Q they have asked. So if you multiply the A1 in both numerator and denominator, how much should we get? This F12 is 1 again because the outer surface can receive all the radiation emitted by the inner surface, inner sphere. But the opposite is wrong, okay? The inner surface cannot get all the radiation from the outer. Q net or Q12 you can write sigma A1 T1 to the power 4 T2 to the power 4 1 minus epsilon 1 divided by epsilon 1 plus 1 by f12 is 1, so the 1 plus 1 minus epsilon 2 into a1 divided by a2. So in this case, you know T1 and T2, both temperatures are known and everything else is known. Epsilon 1, epsilon 2, okay, epsilon 1. Okay, epsilon 1 is how much? Both are black, so both should be 1. Both epsilon 1 and epsilon 2 should be 1 because both are black bodies if the surfaces are black, and R1 R2 you know, So you can just calculate it. So this will directly become 0. This part will become 0. This part will become 0. So this is even more easy because if this parts become 0, only 1 is there. So only the numerator remains. This one you can calculate easily. Can you tell how much it is coming? Only the
R1,
numerator you have to calculate.
what is R1? R1 and R2.
R1, D1 is 0.8. So R1 is 0.4.
635.04.
Which one?
Option E.
A. Have you done like this?
Wait a
Exactly.
minute. Pi is removed. 1995.036.
Yeah, yeah, yeah. So this is the one. So the
Yes,
net, what is the net rate of radiation exchange between the surfaces if they diffuse in gray? So just insert epsilon 1 is 0.5, epsilon 2. Here you just give epsilon 1 is 0.5 and epsilon 2 is 0.05 and just calculate. You should get around this Q. So just write this value down, calculate it later. 1191. What? You got this one, or why the denominator is 0? Sorry, 1. For the previous, for the first question, why this denominator is 1, you got it, right?
yes, yes. For black body, emissivity is equal to
Yes.
1.
Okay, now we'll move to the next question. A solar collector consists of a long duct through which air is blown. Its cross section forms a equilateral triangle 1 meter on a side. So it's one side is 1 meter, so other sides also 1 meter. One side consists of a glass cover. This is glass cover of emissivity 0.9, while the other two sides are absorber plates. Absorber means like just like black body only, full absorbance. Absorptivity is 1, emissivity is also 1. So these other two surfaces are black bodies. During operation, the surface temperatures are known to be T1 is equal to 25 degrees Celsius. This surface is T1, T2 is 60 degree, this and T3 is 70 degree. What is the net rate at which radiation is transferred to the cover due to exchange with the absorber plates? So what is the next net radiation? So for gray surfaces, we have seen this formula. Okay, this one. I is here 1. Okay, how much that one is receiving from the other surfaces. So this formula will use. So basically, inverse 1 means it is in the numerator itself. So instead of this, we can write like this also, AI Fij. All right. So here there are other surface, means there are only two surface. This two, this, if we consider this glass surface as one and other two surface, black bodies are 2 and 3. So others, this J will be denoted by just 2 and 3 only. So this becomes I is 1 here and J is 2 and 3. J1 minus J3 A1 F13. Yeah. Now, what we know from here and what we don't know. So F13, F12 and F13 are this and this surface from, and both are, since it is already equilateral, so we can say these are symmetric also. Okay, so F12 and F13 is equal to 0.5 because they are symmetric surface. Okay, like this and like this. That means how much 2 is receiving from 1, how much 3 is receiving from 1. Since both are receiving, so it is 0.5. And F12 and F13. Okay, this is found out. Then we have to find out what is this J2, what is J3. So J2 and J3 are, since these are black bodies, since 2 and 3 are black bodies, J2 is equal to EB2 J. So EB2 is sigma T2 to the power 4. J3 is EB3 and EB3 is equal to sigma T3 to the power 4. Right? Then epsilon 1 is given. Epsilon 1 is given. A1. Now A1 here it is from both parts. A1 is common, so we can just cancel this A1 from here. Then J2, J3, we know, only thing we don't know is J1 here. Nothing is given for J1. Since J1 is not a black body, since it is just a glass cover, we cannot consider it as a black body. So we cannot say anything about J1. So if I write, if I substitute all the values, I'll get it like this. You can also calculate this EB1. It is not a black body, so it should be sigma epsilon T T1 to, sorry, T1 to the power 4. So this is EB1. Since it is not a black body, you have to multiply this with the epsilon. That is its emissivity 0.9. So F12 and F13 are um, 0.5 and one epsilon 1 is 0.9 is given in the question. 0.5 J1 minus J2 plus J1 minus J3. Both the values are same, so we can take this 0.5 common. So J1 minus J2 plus J1 minus J3. So this becomes 1 by 9 divided by 0.5 2J1 minus J2 minus J3. Right here also EB1 minus J1. Now EB1 is sigma epsilon T1 to the power 4. J2 is EB3, sorry, EB2 sigma T2 to the power 4. J3 is EB3 sigma T3 to the power 4. From here, can you calculate J1? J1 is not equal to EB1 because it is not a black body. Only in case of black bodies is J is equal to EB. So everything is there. T1, T2, T3 is also given. This is epsilon 1. T1, T2, T3. T1 is 25, T2 is 60, T3 is 70. These are in Celsius. You have to convert into Kelvin. Calculate what is J1. Did you get any answer?
J1 is a 650.34.
Okay, I'm here. I'm getting something else.
J1, J1,
J1
J1
only. I'm
650.34.
okay. I have not calculated it, but here it is written some 476.64.
Okay, I have done some mistake. I will check it. If you have.
Okay, you can calculate it later because I'm also getting something else now. I'm getting on 436.92. But what after this? We were going to calculate this q. So this q, after you get j1, you know what is eb1 minus j1. You just insert it here. Then 1 minus epsilon. Epsilon is given 0.9. A1 into epsilon 1. So A1 is given here already. A1 equal to A2 equal to A3 is 1 meter into L. Now they have asked to find out net rate. So this is the net rate Q. In the question they have told net rate, but then in the uh, these options they have given this Q prime. That means per unit length you have to find out. So anyways, if you divide by L, this L will get cancelled. Then you can directly find out. Alright, this you will get it. And the answer for this is 266. This first one. Just note it down and you try to find out it later. So this will be the final answer. After you find out the J, just insert it here. You got it right? So this is just we have used this for gray surface. For gray surface, this equation Q net. We have just equated. This is also Q net and this is also Q net. We have equated both of this to find out what is the Ji. Now once you find out the Ji, you can find it out from here also. You can find it out from here also, the Q net. Anyways, so you can just find out this. Okay, so this is for different geometry. You can find out the view factors. This is one of them. Determine F12 and F21 for the following configurations given using the reciprocity theorem. Configuration is of a small sphere of area A1. This is A1 under a concentric hemisphere of area A2 is twice A1. So first is one rule is there, summation rule. Summation rule is there and another is the reciprocity rule. So in summation rule, F11 plus, since there are only two surfaces, 1 and 2, so F11 plus F12 is equal to 1. And another is F21 plus F22 is also equal to 1. Now in reciprocity rule, we have A1 F12 is equal to A2 F21. Now what they have asked to find out, F12 and F21, these two. Now a surface cannot see itself. That's why F11 should be F11 should be 0. If this is 0, then this should be 1. F12 should be 1. Now from here F21 is equal to, this becomes 1. So F21 should be equal to A1 by A2 into 1. Now what is A1? A1 is whatever, but A2 is given as 2A1. So you get 0.5. Okay, but here this thing is not complete here. Why? Because we have to add one more surface here, some hypothetical surface. Then only it becomes 1. This is not complete here actually. I'm sorry for this. This is not. Because F12 cannot be 1. That's why. Because F12 is whatever 1 is emitting, the 2 is receiving. Here, whatever 1 is emitting, 2 is receiving, it is fine. But this part of the surface, these radiations cannot be received by A2. So this cannot be true. This is false. That's why this is to complete this whole thing. We are considering this as a hypothetical surface, which is 3. Okay. So we are adding one more surface just for to complete this thing. So F13. If we add one more surface, then it becomes 1. All right. So okay, let this remain here. So if I write this as 0, then F12 plus F13 should be equal to 1. Now this is anyways right. If I consider between two surface reciprocity rule, between 1 and 2, I can always write this. So but here F12 is not 1. So I have to write it like this, F12. Now 0.5 into F12. Then we also have this F. Okay, because of this symmetry, there is a symmetry here. This F12 and F31 are same. F12 and F13 are same. Why? Because whatever 2 is receiving from 1, 3 is also receiving from 1. So if I write F12 is equal to F13, then this becomes 0, and both summation of both is 1, then this becomes 0.5. Okay, so anyways, here 0.5 into 0.5, if we do, then it becomes 0.25. This is F21. So both are 0.5. So 0.5 and 0.25. This should be the answer. You got this question? First is when I did like this. You got it right? Okay, let me revise it once more. First, when I did like this, F12 plus F11 plus F12 equal to 1. This this anyways, this always 0. Surface cannot see itself. Always F22, F11, F33, Fnn is always equal to 0. It cannot receive radiation from itself. So here in this case F12 becomes 1. But from the geometry we can see that this can never be 1, because whatever this A1 is emitting, all of them, it cannot, this part of the radiation A1 is radiating, it cannot receive them. So it can never be 1. So what we have done is we have considered another surface here, which is surface 3, and we have added there, and we have made it like this. Now due to symmetry, this F12 and F13 are same, because obviously this is symmetry. We can understand this part of this half of the part and this half of the part is same. So both should be equal. So both should be equal and both addition of both are 1, then both should be equal to 0.5. Then from reciprocity relation you can find out what is F21, that comes out to be 0.25. Okay, we move to the next question. You can just play around with different shapes. What is the F22 for a long duct, cross section of which is given in the image? Now what happens here? In this case, this is true. F12, how much A is emitting? This whole one is the A1 surface, and this is the A2. Now, if this is emitting like this, the A2 can receive all of the radiations emitted by A1. So we can say this F12 is equal to 1. Now now from reciprocity relation we get this A1 is equal to A1 and A2. Now if we consider this as this is a long duct cross section, right? If means it is like this. Okay, something like this. So this area of this below surface should be just this dimension into this dimension, right? So it is just diameter into some x, you can say, and A2 is, this is half of a circle, so perimeter of circle is 2 pi r or pi d. Here you can write as 2, just pi d by 2. Okay, because it is half circle into x into 1. So x gets cancelled. So it is just 2 by pi. How much it is? How much is 2 by pi? Now F21 and F22, the summation of these both are also equal to 1. So F22 we get as 1 minus F21. So 1 minus 2 by pi. So this is what they asked, F22. 1 minus 2 by pi. So this will come out as 0.36. This is the answer. Is it fine? You have any question? These surfaces are closed. Okay, this A1 and A2, these are bounded. But here it is not. It is like this A1 is emitting something, but all of them cannot be received. So there is a difference between these two. if these are, since these are closed, I mean all the radiations can be it is distributed among themselves only. So the total view factor, it can be considered 1 here. So we move to the next question then. Okay, consider the arrangement of the three black surfaces shown where A1 is small compared to A2 or A3. So this is A1, this is small compared to this A2 and A3. A3 is the uh, curved surface part, and A4 is this whole one, this bottom surface. Upper surface is A2, bottom surface is A4, and this small part is the A1. So here F11 plus F12 plus F13 plus F1. So there are four surfaces, all should be equal to 1. Now these are also all bounded surface. Okay, so we can say we don't need to consider extra surfaces, and the total view factor here is 1. Now F11, obviously it is 0, it cannot see itself, and F14, since F1 and F4, sorry, A1 and A4, they are lying on the same plane, okay? They both are overlapping with each other. So this is also 0. So F12 plus F13 is equal to 1. Now we will use the concept of constant and that coaxial disk, which the formula was given. So this is the coaxial disk. Suppose this small one and this bigger one. Okay, so this was L, and this bigger circle diameter was D. So we got that as F12 is equal to D square divided by D square plus 4L square. So this was 1, the smaller surface was 1, a bigger surface was 2, and the view factor is given, F12 is given by D square plus 4L square. So if you find it out, D square is, how much do we get this if we calculate? It is given as 3 meter, this D is given as 3 meter, and L is given as 2 meter. Can you calculate?
Yes, ma'am. Okay. 0.36.
136. So we got F12. They have asked to find out F13. 1 minus 0.36. This becomes 0.64. This option. And another thing they have asked to find out, calculate the net radiation of heat transfer from A1 to A3 if A1 is 0.05 meter square, T1 is this, T3 is this. So Q1 to 3, right? Like this. All are black surfaces, so you don't require emissivity. Emissivity is equal to 1. Then sigma F13 and A1 t1 to the power 4 minus t3 to the power 4. We need to, in this case, we need to consider the view factor. Okay, since view factor is one of the, I mean, how it will determine how much fraction of the heat radiation it will get. The surface 3 will get from the surface 1. So we need to consider this view factor also. View factor is 0.64 into A1 is given, they have given 0.05 into 1000 to the power 4 minus T3 is 500 to the power 4.
1700.
Yeah, so this is the option already it's given. Okay, the next question is a cylindrical cavity of diameter d and depth L is machined in a metal block and conditions are such that the base and the side surfaces of the cavity are maintained at T1 equal to this, T2 equal to this. So this is the same like we have done one of the question like that. This is D, this is L. The base and the side surfaces, the base and this side surfaces are maintained, and this is maintained at T1 is equal to this one surface 1 is maintained at 1000 Kelvin, and this is T2 is maintained at 700 Kelvin. Approximating the surfaces are black. Determine the emissive power of the cavity if this all the surfaces are black. Then L is given as 20 millimeter, D is given as 10 millimeter, and also F13 is given as 0.05. Determine the emissive power, that is EB. Now we consider this as this surface they have not given. We have considered it as surface 3. Okay. This is 1. The curved surface is 2. And the top surface is 3. Sorry, D2. The emissive power of this cavity is given by this. This is the total net heat radiation. We have to find out what is A1, F13, A2, F23. F13 is already given 0.05. No, F11. This is not required. F13 is equal to F31 is equal to 0.05. Why they are why are they same? Because both are parallel. These are this disk, this F1 is parallel to this F3. and they are of the same area. Okay, so by seeing also you can say, just by looking at the geometry you can say whatever A1 is emitting, A3 is receiving, whatever 3 is emitting, A1 is receiving. Or you can also say from here A1 and A3 both are having the same area because they are just top and bottom of the cylinder. They are having the same area. So A13 is equal to A31. This is equal to 0.05. This is given here. Okay, once you know this, we can calculate. Okay, we don't require this. We require F23 we require, right? So F1, we can also write F31 plus F32 plus F33 is equal to 1. We have to use this. So I have written this equation. So here F31 we know, F33 is equal to 0 because a surface cannot see itself. So F32 is given by 1 minus F31. So this is equal to 1 minus 0.05 and this becomes 0.95. Now F32 is known. Now we can find out F23. So F23 is given by A2 F23 is equal to A3 F32, right? So F32 we know it's 0.95. This is A3 and A2. A3 is this one, A2 is this side curved surface. So A3 and A2 you can find out. Pi r square, right? So it should be pi d square by 4. And A2 is the curved surface. There is pi dl or 2 pi rl. And or you can directly calculate this also. This instead of A2 F23 you can write A3 F32. So we can calculate. You can directly calculate this Q. Q is equal to A1 F13. Now this only EB1 and EB2 are left. These are black bodies. They have said that approximating the surfaces as black. So you can calculate this EB1 and EB2. This is sigma T1 to the power 4. This is sigma T2 to the power 4. Sigma we know T1 is 1000. T1 is 1000 and T2 is 700, right? This is 700. So you can calculate from here. A1 is pi d square by 4 and F13 was 0.05 and this is sigma 1000 to the power 4 plus A2 F23. We can also write as A3 F32. A3 F32. So we can write A3 is pi d square by 4 again. F32 we found out as 0.95 into sigma 700 to the power 4. Calculate it, you will get the answer. D is given as 10 millimeter. Also sigma also you can take on 0.05 into 1000 to the power 4 plus 0.95 into 700 to the power 4. Just calculate how much you get. 'I don't have the answer with me, so you have to calculate.
Show the second slide.
This one?
2.28 into 10 power 11. None of the above.
Okay, I don't know which one is the answer. You cross check it. I mean, you check again later on. Check the
Okay.
calculations again. So the thing is, you have to first, obviously, you have to first understand what exactly you have to find out, and then from there, you have to see what you know. So from here, you know this F13, but you have to find out F23. You have to see what else do you know, what else you can find. Since F13 and F31, since A1 and A3 are same and they are parallel to each other, you can say that this F13 is equal to F31. And from there, how you can calculate F23? Or instead of, since reciprocity has, I mean, this is also an advantage. So you can, instead of F23, you can somehow think then that you can find out F32 also. So F32 and 31, they are almost, you just listen to the numbers, you can directly write this equation F31, F32 plus F33 is equal to 1. So you just have to practice it little bit and then you can get the view factors. What is it? And rest is you just,
From exams questions.
yeah,
So there are lots of geometry. So we will solve around 10 to 5 questions of different geometry of each geometry.
okay.
So it is first. It is a what we say.
You're asking me to come with more questions with of view factor like that or
Yes, yes,
okay.
yes, yes.
Okay. Mostly the questions, if you get something like this and all, I mean, which is outside, just like this one,
Yes.
just like this one, if there are um, some surfaces which are extending and it's not getting, in those type of surfaces, you have to add, like this one you have added, we have added. So, okay, I will try to come with more questions on view factor. I'll come up
Okay.
with more geometries then. But for today, this is what I have. Okay, and we'll see in the next class. I think 2 hours is done.
Okay.
Yeah, I'll come up with more questions. Okay. Okay. So For today, we stop here. So thank you, everyone. I'll just leave.